Okay. So we ended last time with me essentially spitting out the three equations of motion that govern spin 0, spin 1/2, and spin 1 particles. Yes?
This was not your hands.
Yeah, you put it there. So I repeated those on the board up here. We've got the Klein-Gordon equation that describes the spin 0 particle. We've got the Dirac equation, and then there's the adjoint Dirac equation, but I'm just going to work with the Dirac equation that governs spin 1/2 particles or spinners, and the Proca equation, which governs massive spin 1 particles. And of course, you can take all three of these equations and set the mass to 0, and you still have something non-trivial left. So these are all good descriptions of both massive and massless fields, actually. Although if you expand around a 0 field background and you just look at an excitation or a perturbation, then the perturbation is governed by these equations as well. I'll say more about that later. I'm just wanting to be honest with you. Okay, so so you did something curious in your homework, right? You took the Dirac equation and you showed that the Dirac equation is not infinitely disconnected from the Klein-Gordon equation, but actually, by manipulating the Dirac equation, by writing this as an operator acting on psi, and then acting on that with the adjoint Dirac equation operator, which still gives you 0, because if something's 0 and you act on it, it's still 0. You should have showed that the spinners that are the solutions of the Dirac equation also satisfy the Klein-Gordon equation. Now, I want you to, I said this in the homework, and I don't know if you really paid attention, but I want to point it out. How many components does phi have? 1. How many components does psi have? 4. It's four-dimensional spinner in 4 dimensions. Okay, so really and truthfully, this is a set of 4 equations, because if you write psi as psi 1, psi 2, psi 3, psi 4, and these are psi's, they don't look like it, then you write this equation down for psi 1, and then you write it down again for psi 2, again for psi 3, again for psi 4. There's no mixing of the psi components, okay? So in the homework assignment, I made the statement, prove that each component of psi satisfies the Klein-Gordon equation. Okay, and that's what you did. All right? So that's interesting. What about this? What do you think? You think that satisfies the Klein-Gordon equation?
If you oppose the Lorentz gauge condition.
Let's see. So we're going to have to do something that's totally not expected. Like here, you had to multiply this by the adjoint Dirac operator times the Dirac equation operator to get that out. But let's see what we have to do here. So first of all, what I'm going to do is I'm going to take the derivative of this equation. Move the derivative past this constant. Okay, and I know that's still 0 because if something is equal to 0, what's the derivative of it equal to? 0. Yeah, so setting it equal to 0 is fine. All I did was I hit this with a d nu and I hit this with a d nu, but I moved the d nu past the constants. Okay? This thing, Jack, I pulled your card. This thing, what happens if I interchange d mu and d nu?
Nothing.
What happens if I interchange mu nu on f?
You have to wait. It's negative. It's asymmetric, yeah.
Yeah, so I have a symmetric tensor in 2 indices, that is contracted with an anti-symmetric tensor in two indices. What does that give me? I will ask a person. Andrew.
Which one?
You.
Me? Is it anti-symmetric?
If I take a symmetric tensor and I...
Oh, 0.
Yeah, you get 0. Okay? And if that's not clear, if you're summing over all these indices, well, first of all, what are the elements of this with 0, 0, 1, 1, 2, 2, and 3, 3? I have an anti-symmetric tensor. What are the elements with 0, 0, 1, 1, 2, 2, and 3, 3? They're 0.
Is that a definition of an antisymmetric tensor that the diagonal has to be zeros?
Yes.
Oh.
If you represent it as a matrix, you have the stuff up here, and then that's negative, the stuff up here. Because interchanging these two indices is just swapping rows and columns. It's transposing this thing. Man, my word is just coming out badly. And I did say wordage. Anyway, okay. No, but I'll just give you an example. So if you do sum over these, everywhere you have a nu, you have to give the same thing. So this is going to have, among its many components, that one. And it's also going to have this. Okay, I mean, I'm summing nu, and 0 is one option, and I'm summing mu, so 1 is an option. And then later on, nu is 1 and mu is 0, okay? But then I can take this and I can rewrite it as d0, d1, because I can always flip those. But if I flip these, I pick up a minus sign, and then these two terms cancel. And that happens across the spectrum, okay? So this thing is 0. That's a very, very important observation that gets used throughout. So just remember, if I have symmetric tensor, and I contract it fully with an anti-symmetric tensor, the answer is 0. Well, what does that tell me that d nu a nu is? It's 0. Okay, now let's come back here. D mu, F mu nu is d mu a nu minus d nu a mu minus mc over h bar squared a nu equals 0. Wait a minute. If I take this and I apply it to this term, I can interchange the d mu and the d nu, and I get this. But what is that? 0. That's what we just showed. So this term is 0, so what I'm left with is d mu a nu minus mc over h bar squared a nu equals 0. Does that look familiar? Klein-Gordon equation. So it's interesting because after a little work, all three of these, at least at some level, reduce to this thing. So you might ask yourself, why don't we just work with this? It's a pretty equation, it's nice. Okay. Well, what I want to do is I want to motivate why things should reduce to this, and then explore what extra stuff these have. Okay? So why should we expect, and by the way, here I'll flesh it back in, because I can read it. This holds one component of A at a time, so it's 4 equations. Yeah.
Is that like, so we said that like the Klein-Gordon equation, like V is a scalar, but this is a sort of vectory tensor.
Well, that's the thing. Since this holds one component at a time, you can kind of act like each version of this is, it's not acting technically on a scalar because a component of a vector is not a scalar, but it's still just the Klein-Gordon equation acting on a single object, not a vector. Okay? All right. So So why do things act like the Klein-Gordon equation? Well, let's actually explore the Klein-Gordon equation. We should figure out where the hell this came from. So I want you to consider the following expression, which we derived in the analysis of special relativity. That is e squared over c squared minus p squared equals m squared c squared. Or e squared minus p squared c squared equals m squared c to the fourth. Just wherever you want to put that extra c squared is fine. Okay? Now I wrote it like this because you might remember what this actually is. This is the square of the 4 momentum. Remember the 4 momentum has components e over c, whoops, e over c times the spatial momentum. And then when you want to do this, you've got to raise it, and that puts a negative there, and then you have negative e over c times e over c, e squared over c squared, plus p dot p, and then I've got an overall minus sign that I threw in there, so I get this. Yeah, and it's equal to 0, so it doesn't matter. So technically this equation would look like this, but who cares? I can just multiply by an overall minus sign. Okay? Now what is this equation telling us about? Yes?
Well, in its original context, it was referring to relativistic classical point particles, but yeah, such an original context.
Yeah, so this is telling us about the relationship between the energy of the particle and the momentum of the particle in one frame, and how that can be combined and always translated, because you're squaring it, into any other frame, which includes the rest frame, where the only contribution to the energy momentum is the rest energy. Okay? So this is really an equation which is describing the motion of a particle through space-time and its mass contribution. Okay? So why don't we do this? Why don't we let p mu be I h bar d mu? That should be a fairly familiar quantum mechanical substitution. If I replace p mu with I h bar d mu, then this equation simply becomes minus h bar squared d mu, and act on a field phi. So I can always plug a phi in here if I want, and that doesn't change that the equation is 0. Okay? So this becomes, if I replace p mu with this, then this becomes minus h bar squared d mu phi minus or plus, nope, it's plus, oh, sorry, that was supposed to be plus, yes, no, sorry, okay, hold on, pause. This thing is actually p mu, which is minus e squared over c squared plus p squared. And so I can replace this with minus p mu, and if I move it to the other side of the expression to combine it with m squared c squared, then it's plus p mu. So I had a sign error in there, but I fixed it. Okay, so I'm going to let this act on phi, and then when I replace p with I h bar d mu, I get minus plus m squared c squared acting on phi equals 0, and then we just move h bar to where it needs to be. Does that look familiar? What is it? It's the Klein-Gordon equation. So the Klein-Gordon equation is actually just a differential operator manifestation of the mass shell condition, which is the name of this thing. Interesting, no? I mean, in fact, I hope you realize this doesn't just work in relativistic settings. If you go to a non-relativistic setting and say, okay, let's write down the non-relativistic version of a mass shell condition, and that's kind of silly, but it's p squared over 2m. This is the kinetic energy plus the potential energy equals the total energy. But if we replace P with minus I h bar del and E with I h bar d by dt, which is what we did here. Okay, we're just breaking it up into the time-like piece and then the space-like pieces. Then this is just going to become minus h bar squared over 2m del squared psi, and let it act on psi, plus v psi equals I h bar d psi dt. What's that equation? That's the time-dependent Schrodinger equation. Okay, so these equations that are governing the overall energetic momentum dynamics of things are following from these expressions, okay, in both the relativistic and the non-relativistic setting. Okay, well, what is the Dirac equation describing? Is it describing particles which can move around? It's funny, you're going, and you're going, oh, I think so, and you're right next to each other. It's cute. Yes, spinors, fermions, spin 1 particles can move around. So if they have energy and they have momentum, they have to satisfy this. Well, sure enough, the Dirac equation, which is the equation of motion for a spinor, includes this because it can be reduced to the Klein-Gordon equation. So the Klein-Gordon equation is this essential piece of the description of the motion of something, and it's contained in all 3 of these. Here it's the only thing, here it's got a little more, and here it's got a little more too, okay? Well, what we'd like to do now is kind of explore what do these have that's over and above what the Klein-Gordon equation has. I guess I can erase this. Yeah, I gotta erase it. Okay, so trying to keep those on the board. So what this is going to lead us into the discussion of are the degrees of freedom of a system. And I have to admit, there's not a really super clear pronouncement of the degrees of freedom of a system for reasons which will become obvious. It's very different for quantum, it's very different for classical, although I will hybridize classical and quantum. It's very different for continuum field theory versus particle excitations. So I'm not going to give you a complete rendition of this, but I'm going to hopefully hit at things which at least make it clear what these things are describing over and above their Klein-Gordon contribution. So first of all, in a classical configuration, the degrees of freedom, the number of degrees of freedom, is either equal to the dimensionality of configuration space, or half the dimensionality of phase space. Okay? Which is kind of cute because you're like, aren't those the same thing? And if you go and explore the definitions, you'll find there's some argumentation about it. But as an example, if I take one non-relativistic particle, with spin 0, okay, then it's described by, well, if you want to talk about x of t, y of t, and z of t, then you're talking about the configuration space. So how many degrees of freedom does this particle have? 3, okay? Or I can describe it by x of t, y of t. Let's want to do that. Vx of t, Vy of t, Vz of t, which is its phase space. Hopefully you were at least introduced to phase space in quantum mechanics, okay? Well, how many degrees of freedom does the particle have if it's moving in 6-dimensional phase space? 3! It's the same damn answer. It's the same system. You should have the same number of degrees of freedom, okay? If you have n particles, how many degrees of freedom do you get? N of these particles.
3n.
Yeah, you get 3n. Okay? Now, for fields, it's a little more complicated because a field is technically defined over all of space-time. So it's a function which can vary over all of space-time. And a particular model of it is you have, in the simplest example, you have harmonic oscillators at every single point of space-time. This means I can draw harmonic oscillators infinitesimally close together. But of course, it's an infinite space, so there's an infinite number of them. So how many degrees of freedom are there for the scalar field? There's an infinite number. Okay? So that's a big difference between a particle physics story and a field story. Okay? But at this point, I know that the fact that there's a continuum of stuff and that, moving from this object to this object is motion, which involves momentum and energy, I can kind of say those degrees of freedom are governed by the Klein-Gordon equation. Okay? What these have that's extra have to be definable at a single point in space. Okay? So there's actually a formalism that underlies this that was written down by Wigner. Was it Wigner that said that? Yeah, anyway, there's a joke about Wigner, but I can't remember it. But it's really funny. I'm laughing internally up here. What's the joke, Wigner? What's the joke about Wigner? Yeah, I can't. It doesn't matter. Anyway, okay. So, well, wait a minute. So, this field phi is defined over space-time. This field psi is defined over space-time. And this field a nu, and there's a nu in here, it's just, this is a compact way of writing it. A nu is defined over space-time. So the fact that these all vary over space-time is the dynamics associated with their variation over space-time is encapsulated by the Klein-Gordon equation. So what is it about psi and A that is different from phi that makes you believe that they have to satisfy these more fancy equations? Ross.
Well, they have multiple components.
Well, they have multiple components, but
They have non-trivial transformation.
yes, they have non-trivial transformations. This is a spinner and this is a vector. You could do a multi-component scalar, but that wouldn't be very interesting. Okay? So we expect that the information encoded in these is somehow harboring the spin, the non-zero spin of these things. Okay, so now this is a relativistic spinner. This is a relativistic vector. This is spin 0, this is spin 1, but how many components does that have? And this is where Wigner's classification or induced representations comes in handy. So, So Wigner's classification system basically says the following. He says, fix the momentum, okay? And the momentum is governed by the Klein-Gordon equation. So fix the momentum of whichever one of these you want to look at. And then ask yourself, what can you do without changing the momentum? Because what you can do that doesn't change the momentum must reflect the additional structure that are in these. Does that make sense? Sorry, I'm looking at Madison. She's like, take your pants off. Okay.
You didn't have to mention that.
Okay, anyway, all right, so, yeah. All right, now there's a good thing I can say to start, and that is that in fixing this momentum, the counting that we're going to do would be the same in any reference frame. Okay? We can pick whichever reference frame is easiest, but the answer that we get is true in any other reference frame. So this is one of those situations where we work with the simplest reference frame, which is, of course, which frame? Yes, thank you. The rest frame. Okay, because in the rest frame, the form momentum takes this wonderful value. Okay? You don't have to pick the rest frame, but trust me, the rest frame is what you get. And this is only true for massive particles. Massless particles changes the story a bit, and we'll do that later in the course. Okay, so now what I would like to understand is what transformations can I do that won't change that? I'm going to pick a name. Danny. What can I do?
And you can do any sort of second, third, and fourth.
What transformations?
Rotations in those planes.
Sorry, say it again?
You can do rotations in the planes of the second, third, and fourth component of that measure.
Exactly. Rotations in 3 dimensions won't change the momentum. A boost, will that change it? Yes. A boost is clearly going to give, it's going to change this term and it's going to add in one of these terms being non-zero. Okay. Okay, so the freedom that we have after we've removed the freedom from things just moving is rotations in 3D. Okay? So what we want to do is we want to see if we can count the degrees of freedom in 3D. Oh yeah, look at that. Okay. And this is where I'm going to go to quantum land, pull some quantum mechanical results which depend on the classical argument, but I can't make a direct connection betwixt the two. Okay? But it doesn't matter, I'll follow up with a return to classical land. So what we want to do is figure out how many degrees of freedom we have associated with rotations in 3 dimension in a quantum mechanical description of what's going on. Wait, didn't you guys learn about that? Yeah, I think so. I think you know all about it, right? We'll review. We'll review.
Some of us are currently taking quantum mechanics, and they are not,
Okay, that's fine, that's fine.
Yeah.
Have you done angular momentum yet?
Physics.
Okay, well, here you go. We're talking, the transformations we're talking about are rotations in 3 dimensions. And so what we should be thinking about is the conserved quantities associated with rotations in 3 dimensions, which is the angular momentum. Okay? All right. So I'm going to make some observations about angular momentum in quantum mechanics, and then we'll just hit you with the degrees of freedom in just a minute. So first of all, in contrast to linear momentum, angular momentum in quantum mechanics is always discrete. Why? Gabriel.
Why is it always discrete?
Yeah.
Because the operators associated with linear momentum do not commute.
Do the
Because you have
operators,
the-
do the operators with linear momentum?
Sorry,
and-
the operators with angular momentum have like products of spatial coordinates and spatial operators and momentum operators. And so you can't commute to linear momentum or angular momentum operators.
Can you commute linear momentum operators? So why are they sometimes discrete?
Why is linear momentum sometimes discrete?
Yeah.
Because the energy of the system is such that the linear momentum has to be quantized in order to. What? Because it doesn't mean they have to tell me. What are you looking for here?
Ross, yours is the next card, so you want to add in?
Well, so I'm not sure if, I wouldn't bet my life on this, but I think that the answer is that in linear momentum, unless you impose some sort of boundary conditions, your space is infinite. So there's no restriction. But in angular
Okay,
momentum-
pause. So linear momentum, if the object is free to move along the x-axis and the x-axis is infinite, is the spectrum of px continuous or discrete? It's continuous. If you bound it, and this can be due to an infinite potential or whatever, but if your x-axis degree of freedom is finite, what is px? It's discrete. Okay. And I mean, this is just like standing waves. You know, if you want to put a wave in here, you've got to satisfy the boundary conditions, and so now you've got a discrete collection of waves. Whereas here, there's no boundary conditions you have to meet, so you can put in waves of any wavelengths you want. Okay? Continue.
But when you're talking about angles, the angles are limited between 0 and 2 pi.
Yes. So when you're talking about rotations, the transformation parameter range is always finite. So really, when you're looking for whether things are discretized or non-discretized in quantum mechanics, what you should be looking at is the range of parameters. If the range of parameters is infinite, then the thing's going to be continuous. If the range of parameters are discrete, it's going to be, or sorry, if the range of parameters is finite, the spectrum's going to be discrete. But for rotations, you're screwed. Because rotations are always finite, and therefore have a discrete spectrum in quantum mechanics. Okay? That's our first observation. Now, there are two types of angular momentum in quantum mechanics. There is the orbital angular momentum, and the spin angular momentum. The orbital angular momentum you can define in terms of r cross p. Okay. How do you define spin? Is it r cross p? No, it's not. Okay, so orbital angular momentum is the angular momentum we get if something is, for example, it doesn't have to be moving in a circle, it would be moving in a straight line, but we usually apply it to situations where you're dealing with an electron and a hydrogen atom, for example, but you have your r vector coming from the origin, you have your momentum vector. You define the orbital angular momentum L in terms of the cross product of those. The spin, though, is the spin of a particle. It has nothing to do with motion through space-time. Okay? It's just a property of the particle. A very big difference between orbital momentum and spin angular momentum. First of all, there's a similarity because they both behave the same way energetically. Okay? For example, if there was a charge associated with these things and there was a magnetic field, a charge moving around in a circle is going to respond to a magnetic field, because a charge moving in a circle is going to create a magnetic field which will respond to the external magnetic field. But if you have a particle with spin and it's charged, then this is also going to create a magnetic field which will respond to an external magnetic field. So these things are very similar, but they're very different because, for example, if I have a particle that's got an angular momentum L, can I change how much angular momentum it has? How?
Flick it.
Huh?
Flick it.
Yeah, flick it. Boom! Now it's shooting off this way, and damn it, it's going to have a new angular momentum. What about spin? Can you change the spin of a particle? You can't change the magnitude of the spin. You can change the direction, but you can't change the magnitude. Okay? This is, I mean, I don't know how clear people are about the difference between orbital and spin angular momentum, because after all, like, they're treated with a lot of the same math and they got a lot of the same conclusions in quantum mechanics, but at the end of the day, you gotta remember this is a damn different thing than this. This is the mysterious property of a particle. This is just, I'm just gonna talk about it moving in terms of angular momentum instead of linear momentum. I can interchange those two. You can't interchange this with linear momentum. Okay? All right, so I'm going to write some stuff down, and then we're going to turn to, or return to classical. So if you have a particle whose spin is 0, and that's the magnitude of the spin, then what are you going to get if you go and measure the z component of its spin? 0. Okay, so spin, and it's actually s squared, and as z, these operators commute. So this is a set of operators whose eigenvalues describe a state. Of course, the eigenvalue of this doesn't change, but the eigenvalue of this can change. And for a given particle, there's only one value of this, but there could be more than one value of this, which we'll see in just a second. So now, if I have a spin, a half particle, and I measure the z component of its spin, what values can I get? Yeah, plus or minus 1/2, and that's actually times h bar. Okay, and this is 0 times h bar if you really don't want it to feel lonely.
Can we also get 0 for a spin half?
No. Okay. However, since you really want 0, if I'm using a spin 1 particle, what values can I get for spin, the z component of spin?
0, 0 plus or minus h.
Okay, times h bar. Okay. Now I have an interesting question for you. and then I'll come back to this. S squared, that's this operator up here. It actually has eigenvalues s times s plus 1 times h bar squared. Okay? Where s is 0, 1/2, 1, etc. S squared is therefore always larger than sz squared. Why is that the case?
It's all of, it's SC, SX, and SY, right?
S squared is?
That big S, yeah.
Yeah, but what if, I mean, s squared is sx squared plus sy squared plus sz squared. That's what it is, okay? So how would I make s squared equal to sz squared? Equal. How would it? Yeah, I just set these to 0. So I get the particle spin, oh, sorry. Damn. Set those to 0. Right? Isn't that what I?
So why can't the inequality be greater than or equal to?
Yeah, that's a good question.
Because those must not be able to be zero.
Because what?
Well, those must not be able to be zero. then.
Why not?
Because S can't be equal to SC. Or S squared, I mean.
Is it because like the S, Z, and X, Y don't commute, so it isn't here next to?
Exactly. Remember, the reason why we use these is because we can't use these. Because these don't commute. Neither does any pair of these. However, if I could set the Sx and Sy to 0, then they would obviously have to commute, but they can't commute, so you cannot set them to 0. So the s squared is always going to have the sz squared part and some contribution from these, because these can't be set to 0. Okay? And that's why the eigenvalues are bigger. That's just a quantum curiosity. It's not really relevant for where we're going. But it's fun, okay? What's more fun than clearing up this shit? Anyway, all right, so, okay. So I'm going to call this a 1 degree of freedom state, this a 2 degree of freedom state, and this a 3 degree of freedom state. Okay, now calling this 1 degree of freedom, calling this 2 degrees of freedom, that is where things get a little murky in connecting the quantum system to the classical system. But, and it's also gets a little murky because, like, you know, you could argue, oh, a spinner has 2 states, spin up and spin down, so I've got something like this. And to specify a spinner state, I have to add in these numbers. These are complex coefficients, so that's potentially 4 numbers. But there's a normalization that you have to do, which reduces 4 independent numbers to 3 independent numbers. And then there's an overall phase that you don't care about, which removes yet another real number, so you're left with 2 real numbers. But anyway, I don't really care about that argument. I just want those numbers. And now, what we're going to do is we are going to see how these equations are governing these degrees of freedom. So here we go. Probably regret erasing that immediately. So I'm going to start with the Proca equation. Naively, how many degrees of freedom should A mu have? How many things should you specify in specifying A mu? 4, yeah, because it's got 4 components.
But you said naively, so I.
Yeah. Well, A mu has spin 1, and this argument is arguing that it should really only have 3 degrees of freedom. So let's see if somehow this Proca equation is going to remove one of these 4 degrees of freedom, leaving us with 3. Okay? So here we go. D mu, F mu nu. And I'm just going to write it again down here. Let's go to the momentum representation. So IH bar d mu goes to P mu, or d mu goes to minus I over H bar P mu. All right, now remember what d mu F mu nu is? Here, I'll expand it here. All right, so this is going to become minus I over H bar P lower mu minus I over H bar P upper mu A nu plus I over H bar P upper mu A mu minus MC over H bar squared A nu equals 0. Okay? Everybody on board? All right, so cleaning this up a bit. Now, in the rest frame, hold on, pause. First of all, isn't this electromagnetism? Why the fuck are we going to the rest frame? Sorry. Why the fucking fuck are we going to the rest frame?
Because we can and we want to, and it's easy.
How can we? Why can we?
There's nothing
Because
Aren't photons massless? A mu describes a photon, right? Ross, save us.
Well, it's because we've said that it's not massless here.
Yeah, we're using the Proca equation of motion, which includes a mass term. So this is not, electromagnetism is this without this term. Okay? So this is massive electromagnetism, which means we can go to the rest frame. Now, my other argument, why did I put a minus there?
Because it's a lower index.
Yeah, because this is the dual momentum. If you have the momentum and you form the dual, it's going to pick up a minus at the time part. Okay?
What's massive electromagnetism?
Well, I mean, first of all, it's where the photon has a mass,
Huh.
and therefore it won't travel at the speed of light. Now, I mean, this is a field theory, and you haven't worked with it in this context, but this is going to become incredibly important because it's going to turn out that the other bosons in the standard model do have mass. So we need this expression, and then when we want to describe electromagnetism, we just set this to 0 and then we go. Okay, but we need this because we do have bosons in the standard model which are massive. Okay? All right, so what we're going to do is I'm going to write down two different versions of this expression. One where A nu is 0, or where the new index is 0, and one where the new index is non-zero. So starting with the 0, we have 1 over h bar squared mc squared A0 plus 1 over h bar squared mc squared A0 minus mc over h bar squared A0 equals 0. How the hell did I get that? Well, look at it. This term involves p mu, p mu. What is p mu, p mu? Look, it's p mu, p mu. So this is p0, p0 plus p1, p1 plus dot, dot, dot. All of these are 0. This is minus mc times mc, so this is minus m squared c squared. Boom. Okay? Of course, there's a minus there, which cancels the minus there, which makes this overall positive. Here, what do you think? Should I have A0 here? I mean, this is A mu, this is not A nu. I'm setting I'm setting nu to 0, but I'm not setting mu to 0.
All of the other components of P mu are 0.
Yeah. I mean, if I take P mu, A mu, that's P0, A0 plus P1, A1 plus dot, dot, dot. All of these are 0 because the rest of the components of P are 0. Okay? So you do get A0 here, and then this is just A0 because we're picking the new equals 0 term. That equation looks pretty simple, doesn't it? You might notice anything nice about it? What does it tell us? It tells us that A0 is equal to 0. All right? Let's check when A is, and when nu is not equal to 0. In this case, I get 1 over h bar squared, mc squared ai, minus mc over h bar squared ai equals 0. Because this term doesn't even contribute if nu is not equal to 0. Okay? Everybody on board? What does this tell us? It tells us nothing. It's already identity. Okay? So now I have a question for you. We should have 4 degrees of freedom, 4 components of this to specify, except A0 is 0. So how many things do we have to specify A? 3, which is what we expected. Okay? Everybody understand that? Follow that? Because now we're going to do spinors. You ready? Okay. So, spinors, and now you have to remember the Wigner classification, because even though this is an equation governing relativistic spinors that have 4 components, once you remove the Klein-Gordon information, you should be left classifying the spinor by rotations in 3D, which is what this describes. So we should expect the spinors, which start out with how many things you have to specify a spinor.
4.
Eight! 8.
Oh.
They're complex. Yeah, they're complex. So they potentially have 8 parameters in them. We should expect this equation to reduce us down to 2. Let's see what it does. Okay, maybe it can do it. Maybe it can do it. All right, so we're going to write the Dirac equation. Remember, d slash is just gamma mu d. Gamma mu d mu, okay? Here I am. Yes, okay. Let's do our usual substitution. to write in terms of momentum, and so this becomes minus I gamma mu p mu psi plus mc psi equals 0. When I plug this in here, I get an h bar, and I just cancel the h bar there. All right. In the rest frame, again, p mu is minus mc 0, 0, 0. So this becomes, oh, look! Minus I gamma 0 times mc plus mc psi equals 0. Okay. All right. So, everybody remember what gamma 0 is?
0, 1, 1, 0.
Times I.
Times minus I. Yeah, these are all 2 by 2 matrices. Okay, I'm just not going to write 4 by 4 matrices. So if I construct the operate, so let's write this a little cleaner. I gamma 0 plus 1 times mc times psi. Oh, there's a c. Okay, so if I construct the operator I gamma 0 plus 1, that's actually nice and clean. It's just 4 of the identities. Okay? Now, of course, this is equal to 0, so I can ignore the MC. It's trivial. All right? So if I do 1, 1, 1, 1 times psi 1, psi 2, psi 3, psi 4, then I get the following.
Why did the I go away here? Oh, because the gamma matrix is I.
Yeah. Then I get the following. So here, I'll write this out just so that you don't get too confused. This is what it looks like. So I'm multiplying this. By the way, just so you realize it, this equation does not hold per component of psi, because this matrix is rotating the components of psi into each other. Okay? All right, so if we multiply this out, what we get is the following. Psi 1 plus psi 3, psi 2 plus psi 4, psi 1 plus psi 3, psi 2 plus psi 4. And that, of course, is all equal to 0. So, of course, if I have a relationship between components of psi, then that reduces a degree of freedom. So in the end, this tells me that psi 1 is equal to minus psi 3, and psi 2 is equal to minus psi 4, which leaves how many degrees of freedom? 4. Oh, shit. I have to say, four degrees of freedom in a spinner, which should really only have 2. That really sucks. I'm going home.
Sorry, what's that blue light?
What's that from? Well, I mean, you got, shut up. There's this damn spinner, which is supposed to describe a particle, and therefore, by this Wigner classification scheme, it's only supposed to have 2 degrees of freedom, but Dirac's equation is spitting out 4 degrees of freedom. That sucks. What in the hell is happening? I mean, this is describing a spinner, right? No, it's not. Huh?
Can you read it out of the textbook thing?
No, I'm just going to say it. This is describing a spinner and a anti-spinner. This is where antimatter was discovered, was in the analysis of Dirac's equation. Okay? And that's what we're going to start with next time. All right? See you guys next week.
No, it's supposed.
What?
No,
How was my rep?